zufälligen Zeitpunkten. Mir ist es nie passiert, wenn ich nicht irgendwie mit dem Stift arbeite. Aber gut, es ist halt vieles auf einmal. Ich arbeite normal auch nicht mit einem Livestream. Da kommen mehrere Sachen zusammen. Okay, good. Let's make this silent for now. It's the last regular slot for our lecture, and we may actually not need the entire time, but I won't promise something yet. But we made good ground yesterday, and then next week there's only extra enrichment stuff or questions, but no additional material. We left off somewhere in the middle of the duality part, and just to remind you, we had this idea of that you can take a linear program and try to prove lower bounds, if it's a minimization problem, lower bounds on the optimal objective value. And what you end up doing by finding the best such lower bound that you can somehow construct from the given constraints is another linear program that is always a maximization problem and is in many ways the mirror image of the original LP. And in particular, there's a few nice properties you can prove. Apart from the obvious one that you do indeed get these bounds for the optimal objective value that you constructed it for, you get these complementary slackness conditions. And so I wanted to show those again because they will pop up in the next sections. Now, these in general don't hold for integer linear programs because they're essentially coming from the strong duality, which also doesn't hold in general for integer linear programs, or only for the fractional ones. And so for integer linear programs, technically we only have the weak duality, but it'll turn out that we can still make some use of these complementary slackness conditions, even though we can't expect them to be exactly true. I guess the one implication is still true if you can find feasible primal and dual solutions and they satisfy these conditions with equality, then that implies they're both simultaneously optimal. But you can't expect those to exist in the general case for integer linear programs. Okay, then a brief look at matching and vertex cover. Okay, I rushed over this part. I mean, maybe you know that on bipartite graphs, many things are easier. In particular, vertex cover is in P for bipartite graphs. It's essentially a very simple problem now because you know that you'll either pick something on the left or something on the right, and then the rest is, you'll mostly, if the graph is connected, just have to pick the entire side, and then you can pick the smaller one. There's not that much left of the problem. And an optimization view on this is that the matrices, these graph incidence matrix, vertex edge incidence matrix, is totally unimodular exactly when the graph is bipartite. If you've seen that before, maybe you like that connection. If you've not seen that before, it's not something we'll make further use of. It's a cool tool. It has a specific definition with determinants of submatrices, but there's more algorithmically intuitive characterizations as well. And the key thing is that it implies that you always have this integral optimal solutions for these standard LPs. But again, just for your enrichment, that part. In the next two sections, we'll make further use of the duality theory in approximation algorithms. And the first one, so there's two separate techniques. The first one is called dual fitting. which is, if you want, rather an analysis technique that uses duality as opposed to an algorithm that directly uses it. And we'll see that on the example of set cover as in the past. The basic idea is this, that we have some algorithm. Often it's an algorithm that already existed before we even thought about duality. And the algorithm maintains a candidate solution that is a feasible solution. So it's feasible for the ILP, I should say. It's integral and feasible for the primal solution. So in set cover, it has to be a set cover. But then, or at the end at least, it has to be a set cover. But the guarantee for its bound, we can analyze by taking the bound, the cost of x in the primal LP, and somehow derive from that a dual set of variables. They may not immediately be feasible, but we can modify this set of dual variables, or these values for the dual variables, by scaling them down, and then that scaled down version is feasible. And so you can use this as follows. The optimal actual value is what you're looking for. That's where we're still in this realm of doing the minimization CTX subject to AX greater equal B, X greater equal 0. That's our primal LP, and here, of course, would be in n to the n. If you have the ILP, so opt denotes the optimal objective value of the integral, best integral solution. Since it's a minimization problem, that's only going to get better if you loosen the integrality constraints to be just x greater equal 0. Come on, we have this easy option, so let me just get the two LPs written up separately. So that's our ILP, and that's our primal LP. So the optimal objective value of this one is going to be better than this one. That's CT for some x star, whatever that is. And by strong duality, that's the same as BTY for some optimal dual variable. So the dual will be the will be this one, and then that's the optimal. You could say that's opt of the dual, and we'll make sure that our y, I know this is a bit abstract and unclear. It'll be more clear on the concrete example. You somehow get to these dual variables from your algorithm. And if you scale them down, if you divide them component-wise by some scalar delta, then that is a feasible, dually feasible solution, which means its objective value is going to be at least, at most the optimal value for that LP. So you can continue this inequality chain. And then, of course, you can pull this delta out. So if you rewrite this for your concrete solution, it's going to be still less than your, that's weak duality here. And here you get this BTY. If you pull delta to the other side, you get that this is at most delta times the optimal objective value. So you get an upper bound for how bad your cost for this algorithm will be. And it all depends on how much you have to scale down these dual variables to make them dually feasible. That's the key question you have to ask. And so on our concrete example, the set cover problem, you'll remember hopefully, is a collection of sets over some universe. And we'll heavily use this notation B of E is the set of all indices of sets where this specific element of the universe occurs. So the notation is somehow suggesting that this has to do with graphs. And of course, if you think about the special case of set cover, where it's a vertex cover, the elements of the universe are the edges of a graph. And then V of E would just be all the endpoints of an edge, just the two vertices. But in general, for set cover, this could be a larger set, right? Then we can write the set cover ILP or LP as we want to minimize the total cost. We've seen this before. XJ encodes whether the set is chosen in the solution or not. And we think of this as being 0 or 1. In the LP, of course, it could be fractional. We multiply it with the cost of that set. What's the side condition? It has to be a set cover, which means we have a constraint for every element in the universe, and we sum over all the sets that contain this element, and then in total they have to cover it. And in the integral case, that's a set cover. In the fractional case, it's a fractional set cover. Okay. You can dualize the set cover LP. Then you get this one just by applying the rules or the intuition from last time. So you have some variables YE. And oftentimes, so the way to think about this is that you go from primal to dual mechanically. You just follow the rules. But then it often helps to take a step back and look and stare for a while at this dual LP and see if it tells you something intuitively, because often it does. We've seen for vertex cover, this was particularly clean in that it gave you just the maximum matching. Here for general set cover is a little less clean, maybe. You get something, you want to maximize some YEs, a value for each element of the universe. And what's the constraints? They say if you sum up all the elements in some specific set, then you can't exhaust the cost of that set. So you could, C could nicely stand for cost or for capacity. So you could say that this, the universe elements are some goods, and you want to pack as much of that good as you can. But these sets are somehow constraints of how much you can take from a certain collection of goods in total. And so across all the sets where some element occurs, you can't exhaust in any of the sets the capacity. You could say that's a somewhat natural problem. I think if you just stare at set cover and think about what would be the natural dual problem, it's very hard to come up with the right definition that's both intuitive and correct. But if you do the mechanical dualization, often in hindsight, it's much easier to make sense of this problem or rewrite the problem slightly so that it becomes somewhat more intuitive. Okay, so the dual set cover problem looks like this. The constraints are essentially summing these amounts of each universe elements over a set up to some capacity or cost. How can we use this in making an approximation algorithm? What we'll do is actually not a new algorithm, but it's the same we've seen before, the greedy set cover algorithm. And if you remember from last week or so, the analysis there was this price lemma where we said, so the algorithm, again, just to remind you or make that clear again, we always pick as the next set greedily the one that gives us per element that we cover now with this set that we didn't cover before. So per new element, the least cost. That's the most cost-effective set, and that's the one that we pick, and we do that greedily. And back then we showed that there's each element is covered at a certain price, namely when it's first covered, we compute what's this price of the set we included per new element and fix that. And we showed that this price can be upper bounded because you could have, at any point in time, just taken the optimal solution to cover all that's left. Here we'll see a slightly more fine-grained analysis if you want, although the result is the same. What we'll show here first is that if you take as dual variables the price at which this element is covered, but you have to scale it down. Remember, dual fitting always has to scale down to bridge the duality gap. We scale down by hn, the harmonic number again. Then that's a dually feasible set of values for the dual variables. So intuitively, you should think of the price as the dual variable, but we can't exactly use that because it wouldn't be feasible. So why is the scaling down good enough? If you remember the dual constraint, maybe just copy this so that we don't have to remember. The dual constraints are these only take as much from the good up to the capacity. And now consider some specific set. We'll have to show that this satisfies all the constraints. So let's pick an arbitrary one. And if we show that that's satisfied, that's good enough. And let's say L is the number of elements in this set. So that sum has L terms. Like at the time when we analyzed this algorithm the first time round, let's name the elements in the order they are covered by the algorithm. So whenever you include a new set, the elements that you now for the first time cover, they become the next elements in this sequence. And at the time when we cover the element EI, that's the ith element in total, we don't know how many elements from the set Sj we've already covered, but certainly at most I minus 1, because we've covered I minus 1 in total. So there must be L minus I minus 1 uncovered elements left. If you scroll back or go back in memory to last week, this is very analogous to what we did back then, but we applied it to the entire set of elements, not restricted to one set. All right, so of course that means if we take this Sj now, and we do, because that's by assumption where this EI is covered, or we could have taken that Sj now, we would cover the element EI and essentially the others in Sj at the cost of E of Sj divided by at least that many fresh elements. And so we don't know if we eventually took set Sj, but the price that we paid for EI can't have been higher because at least we could have picked Sj. Okay. And the actual set that we choose here, this Si star, is only better. Now, if you remember what that means for our variables, that's just scale down. So same thing divided by harmonic number. And now again, look at the dual constraints. So we're continuing them from there. We take the sum of the YEs in a specific set. And I'm going to rewrite that to have indices in the order at which the elements are covered. So we assume here that Sj consists of the elements EI1 up to EIL. There's some ordering of the elements, or there's some indices of the elements in this ordering, so that always works, or that always exists. So we can rewrite the sum as going through these indices, m from 1 to L. And now we insert what we know about these variables, namely this part. That's what we use. See, I'm trying to be very low on memory load today. And then you notice this this denominator is essentially just summing up the first m, or is the reciprocals of the first m integers, so that's another harmonic number. And this comes from just going through the elements in the set here always makes this one larger, so we have to reverse the summation, but that's essentially the same as we've done back then in unit 10. And so ignore that things are reappearing below there. That's another harmonic number, the Lth one, and L is at most n, right? L is the size of the set, so it can't be more than the entire universe. So this is below 1. So we get our upper bound by the cost of the set. And that was the dual constraint. Okay, so this is all. That's why there's the end of the proof. And the sneak peek here you already had is if you do this if you show this for all the constraints, that means our scaled down y divided hn is dual feasible. And then with the chain of arguments at the beginning, the dual fitting in general, this part. Copying is so much fun, and it doesn't cost. You derive this part. So we're using that chain of argument, and our delta is hn, so we get an hn approximation. Now, you may say, amazing, we've already known that. But in a way, the algorithm, the analysis of the algorithm back then needed a bit of a magic insight that you consider this price of an element and that you somehow upper bound this. It was much more ad hoc and coming out of thin air. Whereas here, the dual constraints very, very much guide you to do the right thing. So it's maybe a bit less surprising or a bit easier to come up with the analysis in this case. A small extra benefit, but I'm not claiming this is unique to this analysis technique, is that you see you could actually have taken HL as the scaling down if you take the largest of the sets. Because for each of the constraints, we only needed HL divided HN to be at most 1. That's also true if you pick, instead of n, the largest of all the sets cardinalities. There's a slight bit better, of course, in the worst case, not that much. But set cover becomes kind of boring if there's a set that covers most of the elements. At least it's often clear whether that set should be part of the solution or not. So maybe this is, there's some beyond worst case analysis that one could do there. Another thing we can get from our duality theory here is another piece towards the another piece of evidence supporting the claim or supporting the suspicion we might have that we can't do much better for set cover. That this harmonic number is essentially the best worst case approximation ratio we should expect if we don't look at any other instance specific parameters. And so if you phrase that our approximation algorithms can be seen as relying on the integer linear program and its relaxation. So we've shown with the previous algorithm essentially that the integrality gap is at most hn, because we bounded the cost in terms of the optimal LP value. And I mean, this is, maybe I should show that here again, right? This is the bound we get in terms of the set cover we compute is hn times the optimal objective value for the LP. And that, of course, is a bound for the optimal integer linear program. But we really get a slightly stronger result here if you want, or a slightly more insightful one. So we've really shown that the integrality gap is at most hn. And maybe we can also show that it's at least hn, so that the integrality gap is a key barrier as long as you rely on algorithms that somehow use use ILPs, LPs in all the ways we've seen, there won't be a way to improve. And that's indeed the case, or at least almost. There's an example that we'll construct that shows that this integrality gap is at least a constant factor times hn. And the precise thing we'll show is this, and it's exactly as you might want to read it. We will show the optimum cost of a set cover instance in the example we construct is log of n plus 1, whereas the fractional optimal is essentially constant. And so I think that example, that bad example or family of bad examples is kind of insightful in its own right. It's a clever use of linear algebra. So here it goes. We can build this for an arbitrarily large input size, but it has to be a power of 2 minus 1. So there's some L, and we can essentially use numbers of L bits, including the leading zeros. But we don't include 0, so that's important. The universe, as before, by the way, is 1 up to 2 to the L, excluding the last one, so up to 2 to the L minus 1. We'll treat these numbers, so I'll write the boldface I if I mean the vector. We can treat these numbers as a vector, which just consists of the binary digits. So if I have the number, I don't know, what's a good example? Maybe 9. I can write this as 0, 1, 1, 0. That's actually not a nice example because it's symmetric. How about we make it 11? 2 more. So you can write 11 in binary. And then I'll do the boldface 11. That means just the vector where you take the entries in order. The order is actually not relevant for what follows. Okay, but we'll identify the numbers and their vectors in the following. So the sets that we'll define as J for the same, essentially same as the universe. I don't think the 0 should be there. I think it should be 1 up to n minus 1. Is exactly all the vectors I, or all the numbers I, such that the vectors have a scalar product that is 1 modulo 2. All the vectors are binary, they're only 0, 1, so all the scalar products will be integral. And if you take modulo 2, you're just asking, is this odd or even, right? There's maybe a strange definition, but you'll see in the proof why it's useful. The cost for all the sets will be identical. So the whole thing has a lot of symmetry, which is on purpose. The size of each of these sets is exactly n plus 1/2, or maybe nicer would be to write 2 to the L. Sorry, 2 to the L minus 1. And that's also the number of sets that a specific number occurs in. And to see why that's the case, if you take any number j and look at its vector, it might be some arbitrary collection of zeros and ones. The only thing we know in general is that it is not the all 0 vector. That's why it was important to exclude the 0 here. So there is some 1, and maybe I'm looking at the last one. Doesn't matter where it is. I can take I to be an arbitrary pattern on the on all the positions except for this last one. And I can always put the last digit so that the ITJ is 1. I can always fix this. Say I'm doing 0, 1, 0, 1, just making this up arbitrarily. That's fixed. And now there's this position that I cannot fix. For this one, I have to calculate. And so you see, they have a 1 in common on the second position. This zeroes out everything else. So all that's left of this, excluding the red part, is a 1. right, is 1. All the others are zeros. So I have to put the red to 0 to make that a 1. If I had put a 1 here, it would be, the scalar product would be 2, which is 0 modulo 2. So it's a simple proof that no matter what J looks like, as long as it's not the all 0 vector, you can pick all but one bit arbitrarily, and you can always fix it actually in both ways. The red position decides whether it's part of Sj or it's not part of Sj. And there's perfect symmetry because these sets, the way they're defined with I and J are, you can swap them around. That's why if the size of a set is a certain quantity, the number of elements, the number of sets an element occurs in is the same quantity. Okay, so that's curious enough. Now this is enough to show that we have a very cheap fractional solution, because you can just pick a 2 out of n plus 1 fraction of all the sets. They in total will be a set cover because of this, right? The dual constraints were, sorry, the primal constraints is what we need. Is for every element, you want that the sets that are containing this element in total provide at least 1. And that's satisfied if you have that many sets and you set each to the reciprocal. And so the optimal objective value will just be n times for covering all the elements. So it's the number of sets, should be number of sets, right? Why is this n times? I think this should be the number of sets because we're just summing up all the variables. So it's even slightly better. You get an is the number of sets in total. Oh, the number of sets in total is n. So yeah, okay, sorry, it was correct. It's the number of sets, but that is n. I confused myself with the size of the sets, but really, number of sets is for all those j. I think I confused myself here with the indices. This should be from 1 to n. It should be symmetric with the universe. But there's n of them. So we have n times the cost times the variable. And that's roughly 2 plus minus. At the same time, how many sets do we need in any actual set cover, integral set cover? That's a bit tricky to properly prove. It's kind of clear that the sets are really big. So in principle, there could be 2 that just perfectly overlap. The first covers the first half, the second covers the second half, then we'd be done. But the way they're chosen with these bit patterns, maybe you get the feeling that this is unlikely, but there's a nice formal proof. Suppose that there was a set cover that contains only k strictly less than L sets of, say, I mean, all the sets correspond to some numbers. So say these are the numbers I1 up to ik. I'm going to write these as row vectors in a matrix. So that's a k times L matrix then. It has k rows for the k numbers, and the columns are the digits. Because it's a k times L matrix, it cannot possibly have rank L. It has to have rank at most k. There's not much you can do about it. And so if you look at the null space, so a set of all vectors that if you multiply them to A, you get 0, then that's not just the all 0 vector. You get some other vector j, so that the product is 0 modulo 2, right? This is where the whole thing is also the rank, if you want. We're computing in the field F2. Now that means that J, if you look at what this matrix product is doing, matrix vector product, it multiplies vector J with each of these i's and takes the scalar product. And the outcome is supposed to be 0. That means for each of those I1 up to ik, J is not part of the set because they were defined to exactly be the ones where this scalar product is 1. And so J is not covered. Okay. So that means you have to include at least L sets. I guess L is also sufficient, but that we don't care. At least the optimum is log n plus 1, namely L. And so if you take the ratio of log n and 2, you get slightly better. This is log base 2. We wanted log base n, log base e. But then you get this result. So as long as we're doing essentially integer linear programming based tricks, we won't expect something better than this harmonic number approximation ratio for set cover in the worst case. Okay, let's do a short break here. That's all right, the last section. Yeah, I guess I'll write around on CampusWire as well. But make sure if you're registered for the exam that you have some slot booked. Is the slot final as you booked it, or do you still need to change it? Okay, so you stayed with the Tuesday afternoon thing. Okay. Would you find it useful to use the slot? So next week, I want to tell you a bit about this fun paper, but that's not going to take so long. We could have a look at the lecture survey as well. I don't know if there's a threshold, how many people will have needed to fill it out before we can show it. Sometimes the system even completely hides it. I think it's just, since it's just a survey on Ilias, it might show some results, but the student council may not publish it. Anyways, we can have a look at that. And then there's probably still the Wednesday slot left. Would people feel it's useful to meet and have some questions and answers? Or, I mean, I normally don't care if there's a mostly empty room for the lectures, but for the Q&A, it would be useless. That's for sure. Maybe have a think, and I should ask around on CampusWire. Okay. Can I ask if anyone has used LP solvers for some practical purpose? Because ready-made software of various qualities to solve linear programs. They can actually also solve integer linear programs. If they're not too big, they're usually quite fast. So one point about the algorithms so far is that they often, the last one didn't, but some of the others in this chapter, they start by using an LP and then solve that to optimality, and then you start doing something with the optimal fractional solution. And that's certainly fine in theory because we know polynomial time worst case algorithms for solving LPs, but it's not exactly for free. And if you're after some cheap approximation for really big instances, it might not be the best option to rely on a general purpose LP solver. And so there's this one last nugget of a design technique that tries to get around that as well. So use LPs without solving LPs. In the last section of this part, we'll look at the primal dual schema, which is a way to use the duality and the theory of linear programming, but without invoking a black box solver in your algorithm itself. At least that's usually how it ends up working. And so it's both beautiful because it often gives you insights into the problem itself and leads to more efficient solutions or more efficient approximation algorithms in terms of their actual running time. So far, we've been mostly focused on the approximation ratio, and the algorithms range from simple greedy heuristics to let's start by solving a full LP and then rounding something. So you could say it were essentially ad hoc methods, maybe in hindsight justified with arguments from linear programming. And if they rely on a solver, it can be expensive. There is a way to use duality slightly more directly. And I would say against all odds, the kind of best solution often comes from the complementary slackness conditions, which are precisely the conditions where I said, hold on, these are true for linear programs, but they're not true for integer linear programs, at least the one direction. If you have some solutions, some pair of primal dual solutions that satisfy them, then great. They're simultaneously optimal and with equal objective value, but most hard problems will not do you the favor of satisfying these. And so they seem to be of little use, but indeed you can make them useful in the following sense. You can consider some relaxed version of the complementary slackness conditions, and I'll show you in a second more concretely what that means. And then we can try to somehow maintain a pair of solutions that satisfy these relaxed complementary slackness conditions. Curiously though, normally the complementary slackness conditions start with let x and y be a primal dual feasible pair of values, and then if these conditions are satisfied, that's an if and only if the two are optimal. Here we're going to use the complementary slackness conditions, the relaxed versions, and it turns out the relaxed versions don't imply feasibility anymore. So we're working with solutions that are satisfying these modified CSC conditions, but are not necessarily feasible. You'll see how this makes a lot of sense in the example, but still the general, I want to describe the general schema because it is more applicable than just to the example problems. So the primal solution will keep integral, but it may not be feasible initially. For the dual, we don't care about integrality, but we want to keep it feasible. And then we use the complementary slackness conditions to guide us where to make changes. And so we're trying to make x more feasible, and that means we're going to make y not satisfy the complementary slackness conditions, and we let those guide us how to adjust things. Okay, it's a bit vague. The cool thing about this general theme is no matter how you do it in details, if you maintain this dually feasible y, that's always going to be a certificate for how far away from optimum your solution x is in the end. You have to keep going until x becomes feasible, otherwise it's nothing, it's no solution at all. But once x becomes feasible, if you've maintained a dually feasible y, then that gives you a bound on the optimum. And so oftentimes you can a priori guarantee that you're getting a certain approximation ratio. Okay, let's see this in a bit more concrete. First of all, these are the complementary slackness conditions as we had them before. So for standard LPs. And again, standard LPs, just to have them here again, are these two. And so if you look at what the complementary slackness conditions say, they're essentially pairing a variable in one problem to a constraint in the other problem. And remember, these are, from the way we dualize, this is very natural that you would get this pairing. Because a variable in the dual, let's start with this, a yi here, is essentially the multiplier we put on the constraint, on the ith constraint in the primal, and vice versa, because, okay, I never said this, but if you take a problem and dualize it, and dualize the dual again, you get back the primal. That's something I never said, but it is true though, nevertheless. Okay, but it's natural in this case, so y was the multiplier for the ith constraint in the primal. I think I'm always going to denote this as the primal, this as the dual. So it would help if the p wouldn't look like a d. And vice versa, so x can be seen as the multiplier of the jth dual constraint. And here, this is just one of the constraints where you replace the greater or lesser equal with equality. Okay, that's complementary slackness. And the conditions say, well, there's two options how a solution can be tight and optimal. Either the multiplier I'm giving to the constraint in the primal is 0, so I'm gonna kill that constraint, or it's going to be satisfied with equality. And if you think, well, you can tie it back to extreme points, and so maybe I'm not going to get into the polyhedral theory again. But clearly, these constraints are a stricter version of the constraints in the original problem. You replace the lesser equal with equality, so they still imply the original constraint. They're just more strict. Now, the relaxed versions that we'll look at, they replace this strict equality here with a bit of slack. So I really wish we would have those on the next slide as well. There's two parameters, alpha and beta. So for the two primal, for the two pairs of constraints, we allow a different fudge factor. For the first one, we take this constraint that used to be equal to c and say it's at most c, but at least c divided alpha. Okay. And so you see that's still somewhat still refines this constraint here, but leaves a bit of slack, so it doesn't require it with equality, it requires it with a slack of alpha. For the second part, we also have that this, so that's a b, not a 0. Here also you have the constraint ax greater equal b, but we don't require equality anymore, just not too much too far away from B, not too much bigger. Okay. And the core of the primal dual schema is if you have X and Y, a pair of primal dual feasible solutions. And this can mean in an ILP or in an LP. Both works same way now. Whatever problems you're looking at, if they satisfy these alpha beta relaxed complementary slackness conditions, then you get a quantified version of weak duality if you want. The cost of the CTX is at most alpha times beta times this dual cost. Okay. So weak duality would be, strong duality would be equal. And weak duality would mean the minimization problem is greater or equal this. And now we're getting something in the opposite direction, so we sandwich CTX between BTY and alpha beta BTY. The proof for this is just from computing from the definitions. It's relatively boring. You take CDX. Now you're going to use on C your complementary slackness condition, this part. If you multiply by A, then you get this A alpha times, sorry, multiply by alpha, you get alpha ATY for C, and the X is where it is. Then you expand the transpose. Then you have AX, which you can just bound again with this one by B beta times B. You replace that. And then you just swap things around. Beta is a scalar, so you can move it to the beginning. Okay? Trivial proof. But the point is, if you can somehow make these relaxed complementary slackness conditions hold until you get some feasible solution, then you get a guarantee for the approximation ratio. Cool. Let's finally see this in action. If you look at our set cover LP and dual LP, you get the complementary slackness conditions like this. Either the variables is 0 as always, and then you have the dual constraint. We can't pack, I think this was always an E. Doesn't matter, but yeah. So you kind of can't, you're packing, so the true complementary slackness conditions is you pack exactly as much as the capacity of that set. And for the primal constraint, you cover exactly with 1. In general, this will not be possible to fulfill with integral solutions. So we relax it, and we pick alpha as 1, and we pick beta to be f, the frequency of the element, the maximal frequency. And in this case, it just makes this, second part trivial, in the sense that all we're asking for here now is if you sum up all the sets where an element E occurs in its variable, it should be at most f. But if you keep the x chase below 1, that's always going to be satisfied, because we have at most f sets where this occurs in. So it's kind of, we're making that second condition completely trivial. But hey, that's fine. Trivial conditions are easier to satisfy. And in the end, we're going to aim for a factor f approximation, right? Alpha times beta is just f here. So that's what's going to pop out. And then you can do the following cute algorithm. That's the primal dual set cover approximation. F is the global frequency, so the maximum number of sets that any element occurs in. We initialize our two solutions, x and y, with the all 0 vector. And T will be the elements, part of the universe that we still have to cover. And as long as some elements are not covered, we take some element. And now there's no greedy heuristic or something like that. But instead, we take the dual variable, the ye, and we're trying to pack more of that element. And so if you do that, there's going to be some point where, at least for some set, you're going to hit this this constraint with equality. Right, so the YEs, you can make them bigger, but at some point you're going to have, the constraint was less or equal, at some point it will be exactly equal for some sets, okay? You keep doing, for this single variable, you increase it until you hit, for some sets, the boundary, the threshold. And then you look at all those sets where this is now satisfied with equality. So this is the first part of the complementary slackness condition. So if this part is satisfied, that means we no longer need x to stay at 0. Remember, we initialize x and y all to 0, which means I really wish we had these on the slide. This is stupid. Let's do that. Chunk. And maybe here. So making sure these are always satisfied is trivial if you say x and y are all 0. Then the first part always satisfies the whole thing. But then we don't make any progress towards a feasible x. So we take one of the y's, we make sure that we're trying to satisfy the second part by raising y. And once it hits exactly the upper bound, we're free to make xj to set that to 1. And that's what we're doing, right? We set xj to 1, we remove all the elements from T that are now covered by Sj, and then we repeat. So in a way, it's still a kind of greedy algorithm, but the greed is now with respect to this dual variable. And that way it's a bit more careful than the original greedy. It's an F approximation, not just this Hn. Well, okay, they're, I guess, in general incomparable. So we keep doing this until there's no element left that's not covered. And so this is an F approximation. And there's not much to show. The key thing here is that the proof becomes much easier with this setup. The algorithm only terminates when X encodes a set cover. Otherwise, there would be some elements in T left. So at the end, X is primarily feasible. And when we have some element that is included, we only include it when at the time this the dual constraint was satisfied with equality. That's this CSC1, as I called it in the proof. So if that's satisfied with equality now, we're actually never going to change it. That only depends on the elements YE for elements in this set, and we only ever change YEs for elements that are still in T, but we've removed all the elements from Sj. So this was true now and is not going to be modified. So we'll keep that at equality. And so that means our XY pair at the end satisfy these 1F relaxed complementary slackness conditions. And so that's all we really need, because then we can use the previous lemma for getting the approximation guarantee. And here it's a factor F. I guess we would need to argue that Y is feasible, but we keep Y feasible initially and throughout. Unlike for the primal, the dual problem here, yeah, this bumped around weirdly. For the dual problem, setting all Y's to 0 is a feasible solution. And so it's initially feasible. We never bump it above the capacity, so it remains feasible. And so that's a pretty slick and short proof of this fact. And a similar kind of, you can apply the same thinking to other problems. It's much more versatile now if you think about it, because all we need is really some LP or IRP representation of the problem. And then much of what we're done here is guided from the ILP and doesn't need problem-specific insight. Apart from which alpha beta to pick, that's the only part. And that is it for approximations. We've seen a lot of small examples. So I wanted to list the different design patterns again. There were two based on rounding. Either you do some simple thresholding, or you do some randomization and coupon collecting. And we've seen today, to complement those two methods that use the duality theory of LPs, either to just analyze an algorithm that we've somehow come up without, or to specifically from first principles start with the primal and dual problems and devise an algorithm from there. That brings me to the end of the approximation chapter, and also the end of the material for this term. So thanks for staying till the end, and we'll see each other for the fun lecture for enrichment next week. Juk.